Yes, so this is about the impact of AI on our education. And it's actually not going to be so much about the work I have done, but more about the work I'm going to do or other people are doing at this moment. And you'll soon see why. So I'll give a brief intro to some of the projects and initiatives around AI in education in Utrecht and in the Netherlands. And then I'll talk more about how AI can impact and then I will focus on programming related education, but I think it's probably wider than that. So I want to mention a number of projects and ideas from my background. So I've been working on technology for education since 2005, so more than 15 years already. And for a long time, I've worked on technology to support students when they are solving exercises, mathematical exercises, logic, statistics, many of those. So in the middle of the screen here, you see IDs, feedback services for intelligent tutoring systems. This has been the main focus of my work for 10 years or so. And we've supported many exercise environments, one of which appears on the top right, that's AskL. That's a tutoring system for learning functional programming. So we're teaching Haskell here at Utrecht University and many other universities, and this is an environment in which you can practice with beginners' problems. And when you start practicing, the environment can give you hints about how to proceed when you're halfway a solution, or it can give feedback on the partial solution you've already edited in the edit window and say what's wrong about it or give hints about how to improve it. Well, to test these environments, we've also worked very recently on collecting data sets of steps students take when solving exercises. You see this at the bottom of the screen. There is a very tiny example. On the left, you see public int, factorial int, and then if, and then the next step, the student added a return statement. And what we wanted to do is to try to collect entire sequences of the steps students take so that we can determine how to give feedback at each position, how to give hints, how learning environments deal with these steps students take. So we started on this, but there's still a lot of work to be done there. About the other three images that appear here, I'll have separate slides. So the next slide is about environment, which we developed here at Utrecht University to practice communication skills with a virtual character. We started with this 10 years ago, but since then we sold it to many other schools and companies as well. So now it's a startup company that sells this software. And in the theme of this conference, there's also now a VR environment in which you can practice communication skills. So it's not just a 2D virtual character, but also VR environment. This application would profit. It doesn't do so yet, but we're working on this from a number of AI applications, one of which is when you practice communication skill, when you, for example, have to give bad news to somebody, the virtual character will become angry or sad or disappointed, and that has an effect on the player, of course. The player becomes, anxious. And one thing we would like to do is to measure the effect of the virtual character on the player, and then use that effect to go further in the scenario. So the scenarios here are kind of discussion trees, dialogue trees, which you walk down. But if you take the emotions of the player into account, this becomes much more challenging. So that's one of the things we want to look at. Another thing we want to look at here is, so we're talking now to a call center, which has hundreds of thousands of taped dialogues with clients. And we would like to use these dialogue, this data set, to compare with the scenarios we have in our environment, and to maybe try to optimize the scenario so that we can deal with many more of these discussions of clients. But this is future work. And then if you look at the local landscape, I would call it. In the right top, we have our AI in Education lab. It's an initiative here at Utrecht University. We have several AI labs in which we collaborate with societal partners on AI-related topics. And in the AI in Education lab, we try to collaborate with societal partners, companies or institutions or government organizations on AI and education issues. So that might be related to testing. We have some big testing institutions here in the Netherlands, or it might be related to how to support, improve software for learning mathematics. We have quite a number of mathematics software companies in the Netherlands, and there are more contacts there. So in a way, this is a local instance of a number of initiatives that are larger in the Netherlands. So to the bottom right, you see the Werkgroep Onderwijs. So this is Dutch, Working Group Education. And that's a part of the AI Coalition in the Netherlands. And the AI Coalition is a big project which got a lot of government funding, over 100 million, I think, to work on different AI-related topics. And education is one of them. But it's just one, and it still received a reasonable amount of money, but limited, I would say. If you then look at the top left, NoLai, this Dutch education lab on AI, that's also a new project in the Netherlands, just started, and it got 80 million from the government. So that's a lot of money. And the goal is to, together with primary and secondary schools, with companies developing software for these schools, and with researchers from various universities, to set up experiments in which we add AI-related technologies to existing software in schools, perform experiments with these new developed tools, evaluate them, perform research, and then try to improve them after that. So I'm spending 1 day a week on that from next year, and I'm very much looking forward to it. The attractive thing is that it's really together with schools, really together with companies and the experiments. So it's not just a research exercise, it's also experiments in the real world. And in the middle, there's a recent advice from the, might say, the highest advice council for our government, the Onderwijsraad in Dutch, about the use of AI in education. And that's a very useful report. It warns for the risks that are involved there, the sometimes ethical problems, but it also mentions the possibilities, and it gives several use cases on how teachers may be helped by the use of technology or AI in education. Clearly describes the use of AI in education as something that helps teachers to make progress, not so much as replacing teachers. But now to the impact of AI on our education. I use teaching in the title, so I thought I'd use education here. And let me start with an example. So this figure needs some explanation. This is the submission time distribution of solutions from students to mathematical questions. And so the mathematical question, in this case, for this figure, I use something, quadratic expression divided by another quadratic expression has to be simplified. The exact form doesn't matter. How fast do students answer that question? I looked at this question and I thought it was a bit complicated, so I needed something like, I needed at least a minute, I think. And this gray bar in the middle, that's the 30-second limit for submissions. So in 2010, there was a normal distribution with 30 seconds was a bit quick, but in the middle, you might say. 2011, a bit different to 2012. Well, until 2015, the figure looks the same. But what happens then? In 2016, suddenly the submission, I think with the orange line is something like a couple of seconds. You get 6% there. In 2017, 8.5%. Then, well, it goes on like this, right? In 2021, it's 26.8% of the students submit within a number of seconds. On an exercise where I studied mathematics, I think I needed a minute or so, maybe a bit less. So there's something going on here, right? So what? The researchers here, I have the reference below. What they did is they compared this with the appearance and the number of downloads of a math photo app. So what you can do with this app is you take a photo, a screenshot of your exercise, and the math application solves it for you. And then you can submit the results very easily. So they don't know if these figures are caused by this, but the proof is actually quite, no, there's no proof, but the correlation is very clear. So I think it's basically impossible to submit a correct solution within a couple of seconds. And apparently 30% of the students manages to do so. So here you see the impact this math photo app has had on this. This is a MOOC where, so these figures represent thousands of solutions to these exercises. So it's real, these are real big numbers here. And the good solutions were used for homework or tests. So there is a problem there. And here is actually a similar problem. So you might have heard of GitHub Copilot. It's an environment which helps completing source code. If you are in an editor and you have a kind of description of a task there, GitHub Copilot might help you to suggest solutions. So I talked to a colleague here in the Netherlands from a different institution. They have 200 second-year students. These are good students, but the results on their first programming courses, CS1 and CS2, were approximately the same as the year before. And now they got the results from an algorithms and data structures course very recently, after the release of Copilot. So Copilot has been around for maybe a year now or so, I think. And these students are allowed to solve exams using their own laptop. And suddenly now this year, they have 40% top marks. So in Dutch standards, this is very exceptional to get top mark. And now 40% has top mark. So there's something very funny going on there. So they don't know exactly what, but my guess is that the relation is the availability of GitHub Copilot. And well, let me try some live coding here. Always difficult in a live session, but so here is this is Visual Studio Code, and what I did here is I copied the text of an exam, functional programming exam. So maybe not many of you know how to write functional programs, doesn't matter that much. So to determine if an n-digit number n is a key, now in an entire story here, you create a Fibonacci-like number sequences. Well, doesn't really matter, but the student has to write is keys here. Okay, so let's see if this works. So it's you might have seen the gray stuff here. And so it suggests a solution with the right type. Well, it's up there, so that's not too, so let me accept it. And then it already suggests the solution here, right? And the solution is n should be lm of a Keith sequence n. And actually write a function that takes a number as input and determine, and this is from a abstract level, a good solution. But then I need the key sequence, of course. Okay, yeah, that sounds good typing-wise. So it suggests okay, but it still has a Keith-seq is defined in Keith-seq terms of Keith-seq prime. So I need Keith-seq prime. Okay, and okay, ready. So it completed the solution for me. Is this solution correct? No, it's not correct. So in a way, don't worry. It looks very good, actually. I'm looking at it from a distance. It might be correct, but there are aspects of the solution which are clearly wrong. So, for example, I don't know how well you can read. So the question here is n an element of Keith sequence n? And then Keith sequence n says take while less than n. So this will always return false. So it won't work. But it's close, and I think you need to do a couple of things to improve this to make it work. Okay, so what you need to do is install Visual Code, Visual Studio Code, install GitHub, and you get all these suggestions for free. So people are using this a lot, I think. And I was showing a Haskell example. Here is a Java example. I took a Java exam and I put it in, and it's actually a bit better in Java. So here you see the gray stuff, which is suggested by GitHub. And it doesn't just work for Haskell and Java. So here's another Haskell example. It also works for Python, JavaScript, Ruby, Go, TypeScript, a lot of programming languages. So it's actually pretty impressive, I would say. So what's the underlying technology? You may know about this, you may not. It's in particular Codex. That's a scalable sequence prediction model. And this is not. What this is that when given a number of tokens, Codex suggests the token following on the sequence of tokens, and that's all. And it does this based on a kind of distribution of tokens in a huge data set. For this, it uses this GPT, generative pre-trained transformer language model. And the Codex is fine-tuned on code from GitHub. So it has used 50 million code repositories, and it has done some quality checks that files larger than 1,000 lines are not included, and files shorter than somewhat are also not included. But it has used 50 million of these code repositories and found the distribution of tokens there, and uses that to suggest tokens to users from GitHub Copilot or from Codex. How good is it? Well, this is actually hard to determine. First, the problematic thing, it's non-deterministic. So you might see a GitHub Copilot or Codex as a kind of compiler. You take a text description, including examples or method headers, etc. And you generate code for it. Well, code is in this sense is programming language text, but it's a non-deterministic compiler. So you ask it for a solution, and the next time you ask it for a solution, it might give a different one. The way GitHub Copilot runs in Visual Code Studio is it gives 100 solutions, for example. And some of them are good, and some of them are wrong. So it's not easy to determine how good it is. So the original paper about Codex developed a Python dataset and a kind of a beginner's dataset, I would say. And by looking at 100 samples for each of those problems, 70% of those problems were solved by at least one of those samples. So, well, that's a pretty good number, I think. Although you still have to look at these 100 samples, right? So that's quite some work. In a recent paper, an Australian computing education conference, people did an experiment on a CS1 exam, and GitHub Copilot ended up in the top 20% of the exam. So that's well, pretty good, I would say. Then in the computing science education field, there is the rainfall problem. It's kind of a standard problem to look at when you want to find out how good students are, or what the problems are when students are solving problems. Well, GitHub Copilot was approximately equally good as the students on this rainfall problem, which has been tested in many countries. Then there's another very recent paper, which hasn't appeared yet, which looked at 166 problems of the CodeCheck dataset. It's an online available dataset which you can use to check your coding competencies. And almost 50% of the solutions suggested there were correct on the first attempt, which is also pretty good, I would say. And then what the authors of this paper did, they took the textual description of the CodeCheck problem, and they engineered the description in such a way they thought Copilot could handle it better. And indeed, 80% after this engineering could be solved by GitHub Copilot. So just by editing the text. So I think this has a lot of promise. So what can students, how can we use this to help students? And there's a number of things people have looked at. You can generate solutions for tasks for which students have no solutions. So there's a bad and a good side here, right? The bad side is if you give an assignment to a student for you to assess and to give a grade, you don't want a student to use GitHub Copilot, presumably. But on the other hand, if a student is practicing for an exam, is working on a problem, has tried hard, can't find a solution, can then ask GitHub Copilot to provide a solution. That's an attractive tool. Another thing it can do is generate alternative correct solutions for a problem. That's also nice, of course, so you can compare a solution GitHub gives you to a solution you wrote or another solution and see what the differences are, how they compare, which aspects are better, which aspects are worse. So that's a nice application. And it can be used to repair code. I'll give a few from each of these. I'll give an example later. Then it generate programming exercises. So this goes the other way. Instead of generating a solution, it generates the text of an exercise. It can generate explanations for code, and it can improve compiler error messages. So I'll give some examples here. So this is about generating programming exercises. To make it generate programming exercises, you need to prime it first. So you need to give it an example of what it needs to do. So what you see here is a priming, an example. So you specify a number of keywords, cars, function, parameters. You specify the problem, write a function called speeding check that takes a single parameter speed and prints out you are fine so much if the speed is above so much, etc. So this is the problem text. Then there is a sample solution, def speeding check speed. Well, it's an if statement with these numbers. And then there are a couple of tests that check if your implementation satisfies the specification. So this is the example Copilot gets, and now you can ask it to generate a program exercise. And the only thing you do here is give the keywords, and then the problem statement is empty, and then it fills up the problem statement. And well, what you see here, it write a function called ice hockey check that takes a single parameter called score and prints out you are awarded a penalty for unsportsmanlike conduct. So it's kind of also a fine. So it looks a bit like this car problem, but it's a different problem, but with a similar solution and similar test cases, etc. So the authors of this paper looked at 120 exercises that were generated like this, and well, 3/4 of them were sensible, 82% were kind of novel texts, novel contexts, and almost 80% had a matching sample solution. So pretty good. So you'd have to check them still, but for almost 4 out of 5 were correct. So that was nice. So this was a manual analysis, a programmatic analysis of 240, so a bit more. So 70% had tests, but for only 30% all tests passed. So that's problematic, of course, because then the sample solutions are incorrect, or the tests are incorrect. Explaining code, that's another application. So here is print hello world, step-by-step explanation of the above program. And then they tried this with 20 problems. So 90% of these 20 programs was explained correctly. Then the line-by-line explanations were apparently a bit less correct. And a thing they noticed was that Codex was very good at explaining line by line, but not higher level descriptions of problems. And higher level descriptions, of course, require kind of understanding of the problem. So you can imagine that that's more difficult. Then there's automatic program repair. If you look at the picture to the right, you see a program with a lot of incorrect components. And to the right, you see its repaired variant, which is similar, but it's finding a palindrome apparently. So GitHub has been applied to introductory Python exercises, and it fixes both syntactic and semantic mistakes. And there is a kind of state-of-the-art data set of 286 student programs, and apparently it did better than the average automatic approaches to do program repair. There exist quite a number of these automatic approaches. And then there's the compiler messages improvement or enhancement. Here to the right, again, you see an example of a problem in a program. The standard error message says that syntax error, unexpected end of file while parsing. What GitHub can do is explain this really. So the error is caused because the block of code is expecting another line of code after the colon. To fix the issue, I would add another line of code after the colon. So that's a better explanation of the current problem than that end of file while parsing, at least for beginners. So again, people looked at the data set for error messages and found that there were a lot of comprehensible and explanations in the GitHub provided texts. But the fixes suggested were only 1/3 of the fixes suggested were the actual fix of the problem. So their conclusion was that explanations and fixes are not yet ready for production use, and they pose a risk for students if they follow up on these messages. And you can imagine this, right? If you get this red text here, it's very directive, do this and it's correct. But if that's actually incorrect, that's not very helpful. But this, again, shows promise. Okay, so I think GitHub Copilot and Codex in relation to programming education give a lot of opportunities and challenges. So the opportunities are that it becomes easier to develop sizable software for relative beginners. And there's many other opportunities. It's easier to discuss alternatives, easier to generate explanations, easier to move between programming language. Something I didn't show, but you can enter a program in one language and then you can ask GitHub Copilot to produce the same programming in a different programming language. So there's many things you can do with it, but there is also challenges, of course, and one important challenge is how can we ensure that our students still learn how to program? And the other challenge is, what do students actually still need to learn? If these codex-like tools keep improving at the speed they improve now, I can imagine that most beginners' problems are solved correctly by GitHub Copilot. So they don't need to do this themselves, but of course they still need to learn this, right? So this is a challenge. So together with a team consisting of a colleague, so Johan Jeuring, and a number of MSc and BS bachelor students, so Laurian, Rosa, Sylvain, Roel, Lian, and Mieke. So we are looking at various problems on how to deal with Copilot in our education. So one question is, do students still need computational thinking skills when solving problems with the help of Copilot? So a simple experiment, take two groups of people, one group that doesn't know how to solve problems with programs and one that does. Are they more successful with Copilot? I think the answer will be pretty obvious, but still. But another thing is, what is a good approach to write these texts to provide as input for Copilot to solve programming tasks? So what do we, how specific do we need to be? What kind of components do these texts need to have? So that's I think that's a very fundamental question, actually, because in a way, these texts are now our means to program. In a way, they become a programming language, right? But a very non-deterministic and less well-defined one. Another question is, can we use Copilot to give next step hints to students? So if you look at our curriculum right now, what do we teach our students? What do we say? How do you develop programs? So this is a book from a well-known book from Matthias Valleys and Vindler Flat and Krishnamurti on how to design programs. And they provide a number of steps. First, you need to analyze the problem and go to data definition. Then you need to define the signature, the header, method header, you might say. You need to give some examples. You have to kind of some structure of a function you want to define. This is functional programming, actually. Then you need to define the function, and then you need to test that the function you defined is actually doing the things you want on the examples. So this is a function design recipe, and I think this is very broadly applicable also for methods and in object-oriented programming, iterative program, etc. So this is kind of the things we learn our students, we teach our students now. Another thing we should teach our students is whenever we get a task, we need to determine the sub-goals that are present in the tasks and think about how to solve these sub-goals. So sub-goals are components of complex problem solutions that provide functional pieces of the final solution. And employing sub-goals helps students to solve programming tasks. And it's typically what expert programmers do. They get a large task, they divide it into sub-problems, they solve the sub-problems, and compose these sub-problems, the solutions, to an overall solution. So maybe these sub-goals can help Copilot too. So maybe we should try to formulate our texts for Copilot so that the sub-goals are clear there. So here's an example of such a sub-goal. So given a string, count how many times the ith character from the front equals the ith character from the back. So we gave this first string to Copilot and it gives the wrong solution. And then if you look at the next statement, it says, given a string, check if the first character from the front equals the last character from the back. Then check if the second character from the front equals the second last character from the back. And continue this process until you reach the middle of the string, return how many times the characters were equal. So in a way, you might, this is also more of a code-like description of the problem. But you might also see this as defining the sub-goals or specifying them more explicitly. So we performed a small experiment take a number of programming problems that Copilot doesn't solve correctly. So we took 4 code check problems of different categories, one about lists and one about trees and one about arrays. I don't know the exact, the 4th category anymore. And what we did is we adapted each of these programming prompts, these tasks, in 5 different ways. First, we improved the text. So we just took Grammarly and let Grammarly suggest improvements to the text. We added a function header, as was usually specified in the text of the problem. We added examples or test cases, and in all cases we added 2. So we would add a text, for example, input X gives output Y. We specified subtasks, so divided the problem into smaller problems, and we specified corner cases. So these were the 5 things we did separately for each of these 4 problems. And these were the results we got. So improving text quality didn't help at all. No problem got solved by improving the text using Grammarly. So apparently the texts were already pretty fine. Specifying the function header made Copilot solve 2 of the 4 problems. Adding example added 1. Specifying sub-goals, that solved actually all problems. So all problems were solved by being a bit more explicit about the sub-goals that appeared in the problem. And then the border cases, that was half again that got solved by specifying those. So in a way, when I look at these numbers, I think that's, well, to me it also looks a bit hopeful. Apparently this specifying sub-goals is an important competency you need to solve programming tasks, and also to use Copilot to solve programming tasks. So this is one of the topics we want to focus more on. And here I come to the end of the talk, where I want to show something at the end of the talk. So bear with me for one more demonstration of ChatGTP. So in conclusion, I would say the development of tools like GitHub Copilot forces us to reconsider our education. We need to think about what we need to learn, what we want our students to learn, and how we can use these tools in this learning. And I think the opportunity here is, well, we need to do this, but it's also, I think it's important to do this. It's good to think about what we think is important, what people need to learn about programming. And if we look at CS1-like content, so a first programming course, I would think sub-goals are an important component there. Software quality too. So GitHub Copilot can sometimes generate huge if-then-else statements where our teachers would say, this is not the way you solve such a problem. And another important competency students need to learn is how do you evaluate the quality of software? So you get lots of suggestions from Copilot or Codex, but what's the quality of them? Are they actually correct? Can they be combined with other pieces of code easily, or is that problematic? So it's kind of the kind of things students need to learn are at a higher level, I would say, but important. And my last question is that we haven't seen the last of it. My last conclusion. So recently ChatGTP was released. It's also based on Codex, as far as I understand, but it's better than GitHub Copilot, it seems. And then DeepMind's Alpha Code, which has also recently been at least beta released, I think, seems to again perform better than Copilot. So I think the development is going very fast here. And to just show this, I want to show an application of ChatGTP. So here is a problem statement Given a list of integers, move all negative numbers to the front and all positive numbers to the back, keeping their relative order. I'll copy it and I go to GTP. Let me. All def should go here. Yeah, this is the text, right? Copied. And I'll submit now. There it goes. Yes. Not sure if it's correct, but it looks pretty good. Anyway, I would suggest you to test out yourself and maybe also to take your own assignments you give to your students and show what the result is in these tools. And then maybe think of redesigning your assignments or thinking of how you can use ChatGPT to good use. Okay, thank you.
Switch views again.